So let's look at another quick little example using um, randomness. So this has to do with Latin squares. So Latin square is an n by n uh, matrix, if you like, where you see the numbers from 1 to n once in every row and once in every column. And this, of course, is an old pastime. This is where how this sort of came in, but actually it turns out that Latin squares are useful in all kinds of situations. For instance, in agriculture. So this is actually not just fun. On the other hand, the question I have in mind here is purely recreational. As far as I know, there's no applications for it. So what I'm interested in is what can we say about the determinant of a Latin square. So if we think of a Latin square as a matrix, then it's a square matrix, so it has a determinant. Uh, is there some nice property that characterizes the determinants of Latin squares? And it turns out that at least you can say something about a given number, not one, which divides all possible choices of determinants, and you can actually also say what that number is. And essentially, what you should keep in mind, this is explained in the book, but essentially, what you should keep in mind is that suppose that you add the rows to you take all the rows and add them to the last row. And you take all the columns and add them to the last column. Well, then you will have the same number in all the last rows and columns except in the NN entry down in the rightmost bottom corner. And because of this, the numbers that you get, which is essentially the sum of the entries, this will divide all the entries, and you can do slightly better than that. But I just want to attack this problem in terms of pseudo-randomness, and I have a little program which is called fill, and which takes a partially filled out Latin square and fills it out. So, of course, you have to give it something that doesn't violate the rules of a Latin square, and I'm doing it in the way that I'm just giving it the givens here, which is a matrix that I defined to look exactly this way. The point is that since I only care about the determinant, I don't care about the order in which the rows and columns are organized. So I may as well assume that the numbers in the first row of all the columns are coming one at a time, successively 1, 2, 3, 4, and I can do the same with the columns. So actually, if I want to look at the determinant, I could make a reduction to the case of looking only at um, Latin squares that have been ordered this way. And now there is a program. I don't want to explain exactly how it works, but it's in the book. It takes such a partially filled out Latin square and tries to fill it out using random choices whenever it's possible. So essentially, when I fill out this matrix, I will get new Latin squares this way. And as you can see, if I run this a number of times, the thing that's repeated, of course, is the 1, 2, 3, 4 in both the first row and the first column, but the rest is moved around somewhat randomly. I'm not claiming, however, that this is I mean, of course, when I'm talking about randomness, I'm talking about randomness relative to some sort of distribution over the set of all Latin squares, and I don't really know what that distribution is, because the way the program works, it sort of makes local choices. So it's random in the sense of not being the same every time, but I couldn't really say very specifically what if you have a specific choice, what is the probability that my algorithm would give this. I'm not even sure that the algorithm would give all the choices. So possibly some of the choices will have zero probability. So this is all a little bit murky in the setup, but at least I'll get some data that I can I can experiment with, and then, for instance, I can say, okay, here's 100 Latin squares. I compute its various determinants. These are 6 by 6, and then I get some numbers out. And if you sort of stare at these numbers, you'll see that there is a common theme, namely that they are all divisible by some specific number. So let's be a little bit more systematic. What I'm going to do is I will, first of all, I will sort the data. I will also throw away the signs because the signs don't matter. That's just changing one row and column, or like swapping two rows or swapping two columns. That will still be a Latin square. It will change the sign of the determinant, so that's not so important. And if I do the same with 5 and 7 and 8 and 9, you can sort of see, and even 10, this is going to take a little bit longer, you can sort of see, well, I get lots of numbers in the beginning, there are many repetitions, in the end not so much, but you can very easily see, for instance, here that this is a number which is divisible by 5. This is a number here which is divisible by 5 again, and so on. And so clearly you can start making conjectures about, say, biggest common divisor, greatest common divisor of all these numbers that we're seeing. Now, before I go on, maybe a word of warning. So here in the OEIS, I found the number of Latin squares of order n. Okay, so there's 1 by 1 Latin square, there's 2 by 2, then 3 by 3, 4 by 4, 5 by 5, 6 by 6, 7 by 7, 8 by 8, 9 by 9, 10 by 10. So, when I took 100 out of this astronomical number of Latin squares, this is a very, very small sample. Right, so I need to be very careful about making conclusions from looking at 100 of these, because this is such a small portion that it holds no sort of statistical importance. However, you might still get something out, and of course it's also completely out of the question to look at all of them. There's just too many. Right, so even if I could find it online and download it, it would be just too big to compute the determinants of all these matrices. It's out of the question. But so I'll just, this of course is why I'm using pseudo-randomness. I'm using it because I don't know how to do all of them. So I'm taking a subset, and actually, if I write a little program called MyGCD, for some reason Maple doesn't know how to do GCD of more than 2 numbers, but my little program then sort of runs this through and just takes the GCD of, actually I'm starting with the last number because that's not 0, and then I'm taking the GCD of the last number and the first one, and then of that with the next one, and of that with the next one, and so on. And so you can see that we can actually do a lot better. These numbers are not just divisible by 5, they're all divisible by 275, and for 9 it's 504, 405, 144, and so on. And of course, this looks like something that might be interesting. Right, so these numbers, you can of course try to take them to the OEIS, and you'll not get a hit, but actually that's also because we overdid it a little bit. So actually somebody put in the GCD of all the determinants where they simply computed them all. So somebody, Brendan McKay, is a very famous person in the generation of mathematical data. So they managed to simply find all the Latin squares that are 9 by 9. So this was not the number we just talked about, but something still fairly astronomical, right? This number here. But of course, they're not going through all of them, because just as we saw, without changing the determinant, we can make all kinds of assumptions on the Latin squares. We might assume that they're ordered, and there's even more things that you can do where you sort of say, well, if I replace all the 3s and all the 2s, that's not going to change so much. So there's various kinds of ways that you can reduce this question so that as astronomical as what you had that we talked about before. But this is just put in here without any kind of explanation. And I know from having looked at it a little bit more that what's relevant here is something like you look at the sum of I for I equals 1 to n. Suppose you do this first. Yeah, and I need to do, oh, forgot to tell Mabel what this was supposed to be. So from 5 to 10, say. So I get these numbers, and I think it is true that these numbers always divide those numbers, right? So I can do slightly better. I can do this one divided by this one to have a j here. I get these numbers here, and then this is something which is slightly more mysterious. I don't know if I can find it in the OEIS, but I sort of have an idea of what this is supposed to be. Yeah, you can see it's n if n is odd, or n over 2 if n is even, and actually from a bachelor project that a student of mine did some time ago, I'm pretty sure that this is also something which is provably correct. Right, but so let's not get carried away in this, but the point is that what I'm doing here, in a way, it's very, very naive, right? I'm looking at 100 out of billions of examples, and still with 100 I can see patterns. And this is true in a lot of situations. If you're lucky, if the kind of procedure, the kind of property that you're trying to understand is something which is very global, so it sort of doesn't really matter what 100 elements you take, then this is very likely to work. But of course, maybe you're looking for a counterexample that happens like 1 in a million times. Well, then the probability of you finding it is going to be correspondingly small. So using pseudo-randomness is a tool which works very, sometimes it works extremely well, sometimes it gives you absolutely nothing, and it's very difficult to know going in which case you're in, but that somehow just seems to be the rules of the game here.